Hey everyone, I'm Brian. I'm a developer advocate at Phantom, and I want to talk to you today about versioned transactions. This is a new upgrade to the Solana runtime that we think is a really underexplored design space for developers, and it highlights one of the greatest strengths of Solana, which is its composability and it being a global state machine in which you can reference all these different accounts together. So what are version transactions? What has changed here? So you might have heard a few of these terms being used interchangeably. Version transactions, transaction v0, and address lookup tables. And what's happening here is that now the Solana runtime recognizes two types of transactions. It recognizes the transactions we've always used, but we're now calling those legacy transactions. And it's referencing a new kind of transaction, which we're calling it a version transaction. And the first version of a version transaction is called a transaction v0. And the big benefit to this is that it has something called address lookup tables. Now, address lookup tables are great because it lets us reference many more accounts in our transactions. We're no longer limited to just 35 accounts a single transaction, and previously complex strategies that would require you to send 2 or 3 transactions to be signed by a wallet just to execute a complex swap of some kind now can all fit in a single transaction. So we're going to walk through how this works under the hood and then how you as a developer can add these to your applications. But before we do all that, let's talk a little bit about these legacy transactions. So what I have here is a snippet. It's taken straight from the Solana wallet adapter. So this is Jordan Sexton's example. But if you're a Web3 developer, if you're a front-end developer, you're probably very familiar with this pattern. The way that we create transactions with legacy format today is we have this connection object from Solana Web3.js. We use that to get the latest block hash. We also create this transaction. You can kind of think of this as an envelope, and we kind of seal this envelope with our recent block hash. We'll eventually sign it. And then we stuff this envelope with instructions. And in this case, this is just a memo instruction that says essentially hello world, and we're calling the memo program ID, but this could be also something like transferring LAMP ports or buying an NFT on Magic Eden or doing any of these kind of things that you can do on Solana. So we put all these together, we wait, and we get this signed by the wallet, and then this is serialized and sent across to Solana. So how does this actually work under the hood, and what is the constraint that Solana is putting on legacy transactions that make it such that we need address lookup tables? So if you actually look at what comprises a legacy transaction under the hood, you kind of have two main components. You have this compact array of signatures, and we'll talk a little bit about what a compact array means. And then we also have this message, and this is really where developers are working, and we'll talk a lot about that. But the important high-level takeaway here is that the maximum transactional unit size for anything being sent on Solana is 1280 bytes. But when it comes to actually dealing with transactions that we as developers create, we have a hard limit of 1232 bytes. That's what we're left with when we're creating and serializing transactions. And if you look right here, when this is signed by a wallet, each signature already is 64 bytes. So we're already losing 64 bytes off of this limit every time we add an additional signature. So let's talk a little bit about what this message component is, and we can actually see how much room we have to work with the bytes that are left over. So if I look at this message, it's composed of 4 main components. We have a header, we have a compact array of account addresses, we have a recent block hash, you might remember that from the code snippet example, and then we have a compact array of instructions. So really quickly, just so I can talk about what a compact array is, if you're already familiar with an array, you can think of a compact array as essentially we're showing the length of the array first and then each item of the array. Moving on to each of the 4 components. So the first one being the header. So this one's pretty simple. It's only 3 bytes. Remember, we have that 1232 limit. And this one basically is showing, hey, this is how many signatures are required, how many read-only accounts we're going to have, and how many accounts that require signatures that we're going to have. It's just kind of almost like metadata of the transaction. You can kind of think of it. Then we move on to our compact array of account addresses. So we list all these out. This is a big one. So we separate again by reads and read-write access and read-only access for accounts that require signatures and accounts that don't require signatures. But each one of these that we list out is 32 bytes. And this is where we start to run into issues if we want to compose between a lot of different programs. You see this in DeFi a lot, Jupyter swaps. They have to list all these out. This starts to create problems. And then additionally, we have a compact array of instructions. So we have our array instructions here. And then each individual instruction, that's going to reference a program ID before we reference the memo program ID. It's going to reference that compact array of account addresses we have. It's going to point to indices in that. So that saves us a little bit of size. And then it also has some data that's relevant to the program ID. So all of this put together, like I said, the real issue that we're running into here is that the message that we work with, in addition to the signatures, all have to sum up to 1232 bytes, or it can't exceed 1232 bytes. And when we're dealing with this in legacy transactions, we really can't fit more than 35 accounts. And this is the big pain point. I mean, Solana, you can reference everything. It's a global state machine, but you can't send a single transaction with more than 35 accounts. How do we fix this? How do we add the ability to reference all kinds of accounts together? We can create really rich experiences on Solana. So what the Solana developers have done is introduce transaction v0 and address lookup tables. So there's two main changes that have come with this. One, there's a new program on chain that manages these address lookup tables that we can use, and we'll talk about how we can use that program when we're actually creating transactions. But then we actually had to change this message format so that we could actually make use of these. So there's a hard line between what's considered a legacy message and what's considered a v0 message, and we'll go into some of that. So what do these address lookup tables actually look like? In legacy transactions, we'll actually list all of our accounts that we want before. And so here, we'll have 32 bytes, 32 bytes, 32 bytes. When we create an address lookup table, we'll do that. We'll create something on chain, and then, we'll have this table that's referenced at this address. But then we can just put all these addresses in that actual account. We can reference them then with just these U8 indices. So instead of having to constantly add the same addresses all the time at 32 bytes, we can do all that up front, have that live on chain, and then at the time that our transaction's being used, we can just reference the indices in this table. We can say, I'm going to point to this table at this address, and I want index 1, index 0, index 4. And each time I say an index, that's only costing me 1 byte instead of another 32 bytes. So you can see here an example side by side. We have 5 addresses listed out in both scenarios. The legacy way, we list all 5 manually. 32 times 5, we get up to 160. And in the new way with address lookup tables, we do 32 once for the table itself, the address of the table, and then each individual account, when we're referencing it, we're just using a 1 byte indice. So in this case, we're just adding 5 to 32. We get us 37 bytes. Already massive cost savings. And previously, when we had a hard limit of 35, we now have a theoretical limit using this of 256 accounts in a single transaction. So there's a few other things to consider when we create an address lookup table, and we're going to go through a code example of how you actually do that, but you do have to put some additional metadata on chain. It also needs to be rent exempt. So this is very important as well. So the pattern is we create the lookup table, get it on chain, then we add the accounts that we're interested in it to the table, and then we can reference the table from there. So how do we do all this? Like I said, usually if we're working as a developer with a transaction, we work in that kind of message component. We're going to have to now upgrade what a message can and can't do. And this is where that versioning comes in. So the first version of this we're calling transaction v0. Anything before is a legacy transaction. And how we're actually doing this under the hood is that with legacy transactions, they always left an unused upper bit in the first byte of their message. That was just unused space. Now we can use that space, and we can basically denote the version of this message within that space. So if it's completely left unused, it'll always fall back to just being a legacy transaction. But if we actually use that space now, we can denote that it's a version 0. And you're going to need version 0 anytime you're actually reading or using an address lookup tables. Legacy transactions are not compatible with that. So let's look again, just high level. This was our legacy message. We had header, compact array of account addresses. We had a recent block hash, and we had a compact array of instructions. So what's changed now that we have a versioned message? Remember, we're using that upper bit. We're saying this is different. What have we actually changed? Well, not a ton has changed. The headers kept the same. The compact array of account addresses is basically the same, and the recent block hash is the same. There's two changes. The compact array of instructions has changed slightly, and then we have a new field, which is the compact array of address lookup tables. So the address lookup tables, what is that? Again, compact array like before, we went over what that was, but now we have each of our address lookup tables, if we're referencing multiple here. And when we break it down into what is in an individual address lookup table, it's just a couple of components. You have a U8 account key, an unsigned 8-bit integer, and then you have a compact array of the read and write account address indices, and then a compact array of the read-only account address indices in here. So that's fairly straightforward. What's changed and what's a little bit tricky for some people to wrap their heads around is in the compact array of instructions. So it looks very much the same. You still have the compact array of instructions. Instructions still need to reference a program ID. They need to have an array of account. They need to have some form of account addresses, and then they need to have some data. But the manner in which we're doing this now has changed. So instead of listing out the actual addresses like before, now we're just making use of that table and we're using the indices. So previously, when it looked like this, we had our array of instructions. Each instruction, like I said, had a program ID. It had its addresses, and then it had data. Now when we say the address indices, we're actually pointing at what is in the table. So we have the compact array of message account key indices and compact array of read-write account address indices as well, kind of listed out in here. So all that's theory. How do we actually use this as developers? So this is what I'm going to talk about for the remainder here. We'll talk about the RPC changes, and then we'll get through into actual code examples and show a little live demo of how this actually works. So for the RPC changes, there is a new field that's needed, and it's especially needed on these two endpoints, get transaction and get block, and that is max supported transaction version. If we don't denote this, it's going to always fall back to legacy. We're not going to be able to use address lookup tables. But we want to always put this to 0 if we are set up and using versioned transactions, the recent version, which is transaction v0. So that is a key point to remember when interacting with an RPC. This is actually how it kind of looks like. Here's a curl request that's showing the parameters there. Max supported transaction version being 0. Okay, so let's talk about how do we actually go about sending a version transaction. So there is another takeaway here is that the Solana Web3.js library has changed. So we're going to be using this versioned transactions class instead of the normal transaction class. I saw that if you look back to that snippet we had in the beginning where we're sending a memo, we used like new transaction. We're going to be using new versioned transaction instead. So let's walk through a couple little code snippets. We'll do a little live example at the end. In this case, it looks pretty similar to a developer initially. We're going to create our array of instructions. In this case, it's just a system program transfer from ourselves to ourselves. And then we're going to create, we're actually going to create a v0 compatible message. So this is new. We have a transaction message, and we're going to then compile this to a v0 message using and referencing a lookup account table. We'll get into an example of like actually using this and how it looks like. This is just the high level flow. And then once that's compiled to a v0 message, we can say new version transaction with our message v0. And then this interface for dealing with the wallets is actually the exact same. There's no change if you're interacting directly with Phantom. It's just sign and send transaction. We'll handle it on our side. So this is another snippet, again, how that actually looks if you're using window.solana or window.phantom.solana. This is what this provider is. This is from the Phantom documentation. I'll show it at the end. But yeah, once again, sign and send transaction is the same. the Solana wallet adapter is also set up so that you can start using this as well. Okay, so let's get practical here and talk a little bit about how do I actually build one of these address lookup tables and take advantage of this today. So I mentioned that there's this new program on Solana that manages all this. What's really great is with Solana Web3.js, we can actually use this program to create it ourselves. So I'm going to use this address lookup table program, which is imported from Solana Web3.js, and I'm going to call it create lookup table. We're just going to create essentially an empty lookup table to start. That's the pattern. And once it's created, we're going to add additional accounts into this. So the flow for doing that is I actually create the instruction here and the lookup table address with this method. And then I'll create a message by doing that new transaction message. I'll put my lookup table instruction from here and there. And then I'll compile that to a V0 message, stuff that all into that message into the transaction, send it across the wire, and this is created. Now, this is an empty address lookup table. This is the code that shows how we're going to do that. Once that's confirmed on chain, we can then extend this with accounts. So the way that we extend it is, once again, we're using the same program. Now we have an extend lookup table function at our disposal, or method at our disposal. And I have the lookup table address. This is coming from the snippet before where we actually get this when we're creating that first instruction. We wait for this transaction to confirm. Now we can actually use this thing on chain. And at this point, I can actually start to extend this with additional address. Same format as before. We create a new transaction message. We put that message in a version transaction, and then we send it off to the network. Okay. All that's great. We're just creating lookup tables at this point, but we're not actually using them. Now, how do we go about using them in our applications? Well, we can use the Solana Web3.js connection object that we all know and love again. And this now has a method called get address lookup table. We can just put our lookup table in there and then just basically resolve it, and we'll get all the keys that we can then just loop through and iterate, which are the individual addresses in that table. Then when we're creating and sending transactions, it's once again a very similar flow that we know. We have our instructions. We can add these instructions to a new transaction V0 message, compile that, and put that in a transaction and send it off as we go. So all that's great. If you want to play around with this, we have a Phantom developer sandbox, which I'll walk through now. Also, Jupyter is a really great live dApp that showcases some of this in a really great way. So if I click on this link, this is on our GitHub. This will also be in the description of the video. We put together a code sandbox that shows how you can call all these things in Phantom and what it actually looks like in a console. So you have the code here. This is also available on GitHub. On the right here, this is a little output from Code Sandbox. You'll want to open this in a new window. This is because the way that Phantom injects into the page, it has to be its own standalone dApp. But here I've already connected. I'm good to go. And if I just went out and I sent a legacy transaction, I'll sign into my wallet. All of these are on mainnet, but they're just transfers to myself. So it's de minimis for me to sign. You can see the structure of a legacy transaction here. This is what this looks like. I'm going to now just sign and send a V0 transaction for comparison. This isn't using lookup tables, but just to show you the structural difference here. If I go ahead and hit approve, you can see we have some additional fields in here. There's an address lookup tables field in here as well. That's just not being utilized. So there is a different structure. That's something to be aware of as we went over. Now let's put this all together and create a lookup table on chain, extend it, and send a transaction. So that's what this first transaction is doing. I'm creating the lookup table on chain. We'll see that this is our lookup table address that's on chain. Now this next signature is to extend the lookup table. So I'll hit approve, and then we're going to wait a little bit. And so the reason why we're waiting in this sandbox is because it actually requires one full slot on Solana to pass. And then we're going to be able to reference this lookup table that's been extended to have addresses. If you're a dApp developer, you'll just create this lookup table on your own. Great, it's there. I can hit approve. And now I'm actually referencing something in a lookup table to send a transaction to myself. This is confirmed. And like I said, you can see the code for this all on our code sandbox here. We'll have a link to it on this video as well. If you want to learn more about how you can actually implement version transactions into your dApp, Phantom's docs are a great place to learn about this. You can read our section on sending a version transaction. It goes into every detail about creating a lookup table, extending a lookup table, and then signing and sending transactions through Phantom with a lookup table. We took this guide that was written by Onvit, who's a member of our developer relations team, and we made an entry into the Solana cookbook as well. So if you love using the Solana cookbook, there's an in-depth guide there as well. And if you have any requests or questions, please reach out to us. I can be found on Twitter at bfriel, FRIEL_ is my handle. And last but not least, if you're watching this in January 2023, we're excited to be sponsoring the Lamport DAO Hackathon, and you can win up to 2K USDC for the best project that makes use of these lookup tables. So any questions, please reach out to us. Thank you very much.